So as we've seen, we're putting a lot of what we learned last chapter with our new chapter, and one of the things we're talking about a lot is acceleration again. So to review, what changes in an object's motion can cause it to accelerate. So we know that it could, maybe a text box would be better. Oh yeah. Okay, so we could, an object could speed up, it could slow down, and or change direction. Okay. Any change in the velocity, right? Any change in speed or any change in direction. Number 2, how are we going to draw forces? So we are going to draw forces using arrows because these forces are vectors, right? They have a certain magnitude, they have a certain direction. So the magnitude is going to be shown by the length of the arrow, and then the direction, of course, is just shown by whichever side has the arrowhead. Number 3, if a box has a person pushing with 3 newtons of force on the left side, so maybe now I'll start drawing, on the left side of the box, right? So box pushing with 3 newtons on the left side, and then 6 on the right. Now I'm going to draw that one hopefully about twice as large, right? Because it's twice the magnitude. What would be the net force? So we know when they're in opposite directions that we will subtract. So we'll do 6 minus 3, which gives us a net force of 3 newtons. Also important to include what direction it's acting in. So is it 3 newtons to the right or to the left? It'd be to the left because that one has more magnitude. Great. Number 4, what happens to an object that's experiencing balanced forces? So an object experiencing balanced forces will not accelerate. So depending on if that object is already moving or if it's still, that will kind of make a difference as well. So if it started at rest, it will remain at rest. If it is moving, it will continue moving at the same speed and in the same direction. Okay, so not accelerating, not speeding up, not slowing down if the forces acting on the object are balanced. If the forces acting on an object are unbalanced, so one side is experiencing more force than another side, then it will accelerate. So an object experiencing unbalanced forces will accelerate. If it started, well, really either way, right? So what does acceleration mean? So it will either speed up, it will slow down, and or it will change direction. Okay, moving right along. So question number 6, in which direction does friction always act? So that is a little bit of a trick question because always is usually a pretty strong word, right? So friction acts opposite the direction of motion. So if an object is moving up, friction acts down. If that object is now falling and moving down, friction acts up. If a box is moving to the left, then I don't know if that comes up as left or right to you guys, to be honest with you. Is that strange? Probably to your right. So if it's to the right, then friction will be to the left. I think you get the point here. So opposite of motion. A fluid, okay, so we have the term fluid friction in this unit. So to be clear about what a fluid is, so usually like if you're sick, right, they say like, oh, drink lots of fluids. And so one type of fluid that typically comes to students' mind is a liquid. But fluids can also be gases. So anytime an object is moving through a liquid, so maybe like a boat in water, or if it's moving through a gas or a mixture of gases like the air that's all around me here, then that object is traveling through a fluid and it will experience fluid friction. Number 8 asks, is there gravity between your pencil and your calculator? And the answer is yes, there is. And so they want to know why. So remember that gravity is an attractive force between any two objects. Okay, so happen to have a calculator and a pencil here, not planned. Since these both have mass, they are technically attracted to one another. Obviously, they don't have to be right next to each other. In fact, I could take one to the other side of the world, and it's not like they're going to slowly find their way back to one another. And that's because, so gravity is dependent upon a few things, one of which is the amount of mass, right? The more mass something has, the more gravitational force it has. So obviously that makes sense as to why the Earth has so much gravity, because it has so much mass. So more mass, more gravity. Let's make sure we have that one typed out for you. So yes, since they both have mass, they both have gravity. They both have a gravitational force. Number 9, what force balances out the gravitational force on a book sitting on a counter? So if a book is sitting on a counter or a table, why doesn't the book just fall through the table or fall through the counter, right? That would kind of be weird. We probably don't think about that too much. That's because there is another force that's pushing up on that book to balance out the gravity that's pulling down on it. And that force is called the normal force. The normal force. I thought I had a space. Okay. 10. In what direction does gravity always act? So gravity is always going to act. So you could say downward if you want. If you want to be like super particular, you could say toward the center of the earth, right? If I have an earth in my hands, then the gravity would be acting toward the center of the earth. Or downward. Okay, number 11. What two forces act on a falling object? So we know for an object to fall, gravity is going to be pulling it down, so that's definitely one force acting on it. The other force, since our object is coming down, we know anytime we have a moving object, there's friction acting in the opposite direction. Now, if an object is falling through the air, what kind of friction is it going to experience? So you could say fluid friction, because it's falling through a mixture of gases. Gas is a fluid, yay. But more specifically, you could say air resistance. So air resistance is a specific type of fluid friction that acts on our falling object. Number 12, draw a motion diagram of a ball experiencing free fall. So a ball experiencing free fall. So that means that free fall is going to mean that it is speeding up as it falls. Motion diagram, as we've learned, means I'm going to draw these getting farther apart because it's speeding up. So farther apart. That's about it. You're welcome to add arrows for like gravity is pulling it down, air resistance is pushing up, AR for air resistance. I tried to make the air resistance arrow smaller than the gravity one, and that would be, again, because maybe I'll make it a little longer. Because if gravity is pulling down more than air resistance is pushing up, these are called what? Unbalanced forces. And when forces are unbalanced, the object does what? Accelerates. So this ball is speeding up because these forces are not balanced. Now in our picture for number 13, where our ball is experiencing terminal velocity. So we learned that terminal velocity is when the air resistance pushing up on our falling object and the gravity pulling down, I tried really hard to make those the same size, are equal or are balanced. And so we know when forces are balanced, the object will not do what? Accelerate. So as our ball falls, it will not be speeding up, slowing down, or changing direction. So our ball is now I'm going to want to try my best to draw these the same amount apart. Oh, the bottom of my screen cut it off a little bit. So before we had them getting farther apart because these forces were not balanced and it was speeding up. But now the air resistance and gravity are the same amount, or they're balanced. So our object is no longer accelerating. It's still moving. It's just moving at a constant speed instead of speeding up. Okay, number 14, which force typically causes an object to stop moving? So we know that if an object is moving in one direction, we have a force that opposes that motion. And we know that that force is friction. So if we didn't have friction between our soccer ball and the grass, then the soccer ball would just keep rolling forever because there's nothing to stop it. Number 15, give an example of the law of inertia that isn't in your video notes. So remember, inertia just means that objects want to stay in one spot if they're already at rest, or if they're moving, then the object wants to keep moving at that same speed and in that same direction. So I like to use the example of think about like the rock, right, out in front of the school. It's at rest, and it's going to take a lot to get it to move, right? It has a lot of inertia. Or you could use the example of if you've ever seen like where there's a tablecloth, right, and there's all this stuff on top of the tablecloth, and then they pull the tablecloth out from underneath it, and all the objects just stay on the table, like just drop down a little bit to the table. So that's an inertia too, because you're saying that the objects don't want to go anywhere. They just want to stay where they are. And so they're staying where they are. They're remaining at rest in that example. You may have come up with your own. I would love to hear them. Okay, so continuing on. Number 16. So what unit do we use to measure force? So we already used this a little bit. We call that the Newton. And it is abbreviated with just a capital N. Number 17. The more mass an object has. Got that. Okay, the more mass an object has, the blank force is required to get it to accelerate at a certain rate. So if I have two objects, right? If I have like a basketball and a bowling ball, so not two different size-wise, right? And I want them to both speed up at the same rate, right? I want them to both be speeding up by 1 meter per second every second. So if I push on them, I won't be able to push on them with the same amount of force because their masses are so different. So if I have my bowling ball And so, right, more mass. And I want it to accelerate at the same rate as this basketball, then I'm going to have to push that one with a lot more force. Okay, so more mass is going to mean more force. Right? So the more mass an object has, the more force is required to get it to accelerate at a certain rate, whatever that rate happens to be. Okay, 18. How are mass and weight different from one another? So weight, and one way to remember this is that there's that nice G in it, right? Weight relies on gravity. So if the gravity changes, if you go to the moon, if you go to Saturn, right? If you go somewhere where the gravity is different, then the weight of the object is going to change. Mass, on the other hand, is just saying how much matter is in the object. So mass does not rely on gravity, or it will not change based on where it is, because it's just the amount of matter in an object. So if a person goes to the moon and it says, oh, you only weigh this many pounds now, like they didn't actually lose anything, right? The only thing that changed was the amount of gravity, where again the mass won't change depending on the gravity. All right, and then 19, how are balanced forces different from action-reaction forces? So in both cases, we've got like arrows either pointing at each other or away from each other. So those kind of get a little confusing. So balanced forces will be acting on the same object. So just like earlier on your paper where you had the box, right? And you had the two forces acting on the box. They were both acting on the box. And so if those are the same, we say they are balanced forces. Action-reaction forces, or interacting force pairs, which we said on our pretest, interacting force pairs or action-reaction forces act on two separate objects. So I gave the example in that one of like if I push on my desk pushes back on me and I'm able to roll away. So there's two objects there, right? Me acting on the desk and the desk acting on me. So that's action-reaction. If someone else and myself were both pushing on the desk, like on opposite sides of the desk, then that would be an example of balanced forces because we're both acting on the desk. Hopefully that makes sense. Maybe I'll jot that down in case you need it. Okay, so balanced forces act on the same object. Action-reaction forces act on different objects. Okay, and then 20, give an example of action-reaction forces that isn't in the video. So again, anytime we have a push on one object that leads to a push on the original object, or a pull even. So if you are rock climbing, for example, right, the harder that you push your foot into the hold, then the more the hold can push up on you so that you can step up. Okay. Obviously, you might have had other examples, and that I, again, would love to hear them at another time. All right, thanks for listening to your answers to your video notes questions.